All right, so the next thing that we're going to work on is how do you solve a polynomial that you can't factor? Now, when we were looking at quadratics, right, we started by looking at how do you solve by factoring, right? And then after that, we said, okay, well, now we're going to look at things for when factoring doesn't work. So that's when we looked at like completing the square and the quadratic formula, right? So the thing about those methods is that those are specific to quadratics. Okay, it's a special method that works just when you're talking about quadratics. So if we wanted to look at, say, a cubic degree 3 polynomial, right, then we would have to have a different formula. Like we'd have to have, instead of a quadratic formula, we'd need like a cubic formula, right? And then if we looked at a degree 4 polynomial, then we would need like a quartic formula. Okay, so we'd have to have different like formulas for every degree polynomial. And as you can imagine, that would be a lot to keep track of. And additionally, the higher that you go with your degree, the more complicated those formulas would become. Okay, so we don't really have a quadratic formula equivalent when dealing with polynomials. So instead, we're going to kind of use this alternate method to figure out our solutions. Okay, so we're going to start by talking about the rational root theorem. As you can see, a couple of tweaks have been made. I started filming this video and then I realized that there were some extra words in this sentence. Okay, so what this should say is that if you have some polynomial and it has integer coefficients, so you have to have whole number, right? Positive or negative coefficients, then every rational solution of f of x equals 0. So we had a couple extra words there, just scribble those out if they're on your paper still. So every rational solution of when you set the polynomial equal to 0 has to have a particular form. And what that form is that they have to be in the form p over q. So two numbers, p and q, divided together, okay, where p on the top has to be a factor of a sub 0, which is your constant. Okay, so the constant at the end of your equation. And q has to be a factor of a sub n, which is your leading coefficient. Okay, so assuming that you have like a regular old polynomial and no terms are missing or anything, essentially p is a factor of the number at the end and q is a factor of the number at the beginning. Okay, so that's kind of what this rational root theorem says, and this is going to be the piece that we use to help us. Okay, one more thing that I want to talk about, a theorem and a corollary. So the fundamental theorem of algebra, we've kind of been talking about this. And although I've been saying it's the fundamental theorem of algebra, we've technically been talking about a corollary to it. So I just want to kind of go over what the difference is. So f of x is a polynomial of degree n, where n is greater than 0. So that just means like technically the number 3 is a polynomial because it's 3 times x to the 0, but it's kind of like trivial. So we're saying like, okay, you got to have at least degree 1. It's going to be at least a linear equation, okay? Then if you set that polynomial equal to 0, it has at least one solution in the set of complex numbers, okay? So at least one of its solutions has to be in the set of complex numbers. And remember, the complex numbers include imaginaries, okay? So basically all this is saying is like, in terms of quadratics, it's saying that no matter what quadratic you draw, it's going to have at least one solution in the complex numbers, right? All of these guys, no matter how I draw this parabola, right, it's going to cross the x-axis, right? In which case, those are complex numbers, right? Real numbers are considered complex numbers, okay? Or it won't cross the x-axis, in which case we know that that means that it's got some imaginary solution, okay? So that's kind of our options. So what the fundamental theorem of algebra says is that any kind of polynomial, not just quadratics, they're either going to cross the x-axis or you're going to have imaginary solutions, okay? So that's what this theorem actually says. And then we've got this thing called a corollary. And a corollary is like a math word of saying like, okay, well, because we know this is true, now we can conclude that this is true. So the corollary is that if this polynomial, we're going to say it has to be at least a linear one, right? We look at this and we set it equal to 0. If it has this polynomial has exactly n solution, provided that each repeated solution is counted as a separate solution. Okay, so that's what we've been talking about. If the degree is n, then it has exactly n solutions, assuming that you count any repeated ones as separate solutions. Okay, so like if I had, as an easy one, if I had like x squared, or actually no, let's make it this way. So x plus 2 squared equals 0, right? I know that this would be x plus 2 times x plus 2, right? So you would technically get x equals -2 twice. So what it's saying is that assuming that you count this and this a repeated answer as two separate solutions, two separate zeros, then whatever the degree of your polynomial is, you will have exactly that many solutions. Some of them might be imaginary, some of them might be real. Okay, so that's going to be kind of what we're going to use to help us. Okay, so we're going to use these two things in conjunction. So the first thing that I'm going to conclude is that when I look at this polynomial that's a degree 3, I know that I have 3 solutions. This guy, degree 4, 4 solutions. Degree 3, 3 solutions. Okay, so that's the first piece that's going to help me, and that's going to be how I know that I get them all. Now, the second thing that we're going to do is we're going to use this rational root theorem to guess at some of our solutions. Okay, so again, what this said, right, it says that every rational solution has to be of the form P over Q, where P is a factor of the thing at the end and Q is a factor of the thing at the beginning. Okay, right? And again, we're just assuming it's a normal polynomial. So for this example down here, 12 would be P, that's my constant, okay? And then there's a 1 for a leading coefficient here, that would be Q, okay? So what I'm looking at here, so the first thing that I'm gonna look at is I'm gonna look at factors, okay? So I'm looking at the factors of P, which is 12. So what are my possible factors of 12? All right, well, I'm going to make a list, and I'm going to actually, I think I'm going to make them this way. So I can make a little pair ones, right? I know 1 times 12, 2 times 6, and then 3 times 4. So those are all my possible factors of P. And then my factors of Q, right? Well, it's just 1 times 1. That's it. Okay, but there's actually one more thing we have to consider, right? Is that these are all my possible factors, but they could be positive or negative, right? Like it could be positive 1 and positive 12 or negative 1 and negative 12. Okay, so all of these are technically positive or negative. And similarly with the 1, it could be 1 and 1 or it could be negative 1 and negative 1. So those are similarly also positive or negative. Okay, so that's the first thing that I'm looking at is I'm looking at what these factors are. Okay, so then what my possible solutions are, so my possible solutions, okay, are any number from this list divided by a number from that list. Okay, and because these are just ones, it's going to make this list pretty trivial. So what are my possible solutions? Well, I could do positive or negative 1 divided by positive or negative 1, and that's going to give me positive or negative 1, right? Positive negative 2 divided by 1, that's going to be positive or negative 2. Right? And as you can kind of see, it's really going to work out to be basically the same list that we had for P. Okay? Yes, you have to write positive and negative every time when you're listing your possible solutions. Okay, so these are your possible solutions. Okay, great. Well, what does that mean? Because you're like, but Miss King, that's 1, 2, 3, 4, 5, 6, and then doubled. So that's 12 different solutions. And you said that there's only going to be 3 because it's a degree 3. You're right. Not all of these are solutions. We're not saying that these are all the solutions. We're just saying that if there are any rational solutions, so any kind of a number that can be written as a fraction that's a solution to this, it's going to be somewhere in this list. Okay, that's what this rule is saying. All right, so we're going to come back to how we use that in just a second, but let's do another one of these. Okay, so we're going to do the same thing, find the possible solutions of this where it's going to be a little bit trickier. So in this case, P is going to be negative 10. So I'm going to start by finding the factors of P. So I could do 1 and 10. So either negative 1 and positive 10 or positive 1 and negative 10, right? So some combination where one of them is going to be negative, right? Or 2 and 5, where again, some combination where one of them is going to be negative. So they could be positive or negative. All right, and in this case, Q is 4. So my factors of Q, right, are going to be 1 and 4 or 2 and 2. And again, positive or negative, we're not sure. Okay, so then when I go to make my list of my possible solutions, so again, these are not the actual solutions. These are my possible solutions. Okay, so my possible solutions are factors of this divided by, factors of this divided by factors of that. Right, I wrote them. It's factors of this number divided by that number, and I wrote them the other way when I made my little tables, so I threw myself off for a second. So factors of p divided by factors of q. So positive or negative 1 divided by 1. I'm going to start by just dividing all of these by 1, then I'll divide all these by 2, then I'll divide them all by 4. So I'm being systematic. So 1 divided by 1 is 1, 2 divided by 2, 2 divided by 1 is 2. 5 divided by 1 is 5. 10 divided by 1 is 10. Then I'm going to go back through this list, but now I'm going to divide them all by 2. So that's going to give me 1/2. 2 divided by 2 is 1. That's already in my list, so I don't need to rewrite it. Okay. 5 divided by 2, I need to add that one. Okay, and then 10 divided by 2, that's 5. That's already in my list, so I don't need to write that one again. Okay, and now I'm going to go back and divide all these by my last factor, 4. So I'm going to have positive or negative 1/4. 2 divided by 4 is 1/2. We already have that, so I don't need to write it again. 5 divided by 4. Okay, and then 10 divided by 4, that simplifies to 5/2. We already have that on our list, so I don't need to write it again. So those are all of my possible rational solutions. So I could still have square root solutions or imaginary solutions, right? Complex ones that aren't in this list, but any kind of solution that could be written as a fraction is somewhere in this list. Okay, great. So how does that actually help us? Okay, well, now what we're going to do is we're going to just basically try to find numbers that work. Okay, so I'm going to look at this polynomial, and I'm going to use the fact that we know that when you do synthetic division, right, if you do synthetic division and you get a remainder of 0, that means it's a solution of the polynomial, right? It means it's a factor. Okay, so if your remainder is 0, we know it's a factor. Okay, so that's the piece that we're going to use to help us out here, is we're going to basically use this as a bank of answers to check from. We're going to try some of these answers and hopefully stumble across one of them that works and is a solution. Okay, so it's kind of a pain. It's a little bit inelegant, but it's going to work. Okay, so let's do this again. So I'm going to do factors of p. So factors of p. 20, so I can do 1 and 20. I can do 2 and 10, or I could do 4 and 5. All right, this guy's got a leading coefficient of 1. It's kind of nice when that happens. So the factors of q are just 1 or 1. And again, positive or negative, the whole thing. Okay, so then my possible solutions, I'm going to take these numbers and divide them by 1. And again, if I ask you to list out the possible solutions on a test or a quiz, yeah, you have to write the positive or negative over and over again. Okay, so positive or negative 1. So all of these just divided by 1, it's just going to stay the same. Okay, so from here, it's literally a guessing game. Okay, we've got 1, 2, 3, 4, 5, 6. So we got 12 possible solutions, and we're basically just going to literally guess and check. Okay, that's what we're going to do. So it's annoying, I get that, but that's how we're going to tackle this. We're going to just try things and hope one of them works. But the good news is we get to use synthetic division, which is fast and easy. So 1, negative 8, 11, 20, because I don't have any missing terms. I'm going to start with positive 1 and see what happens. So try it with 1, bring this guy down, multiply, add, multiply, add, multiply. Doesn't work. Okay, so again, what we're looking for is we're looking for something with a remainder of 0. If I don't get that, it's not a factor. All right, so back to the drawing board. I'm going to try another number. I think I'm going to try negative 1 next, right? Because it could be positive 1 or negative 1. So I'll try that one next. So if I try negative 1, that's 1, multiply, add, multiply, add, multiply, add. Awesome. Okay, not a frowny face, smiley face. Okay, that is what we're looking for. Okay, sorry, I kind of cut you off there, you couldn't see. Okay, that's what we're looking for. We're looking for a remainder of 0. Okay, so the key thing here, right, is that this guy, right, the remainder was 0, so it's a factor. That's what I'm looking for. Okay, So I'm looking for a number and I'm just guessing things and trying them until I find one that gives me a remainder of 0. Okay, so what does that do for me? Where am I at from here? So now I'm at a point where I can look at this and say, okay, -1 is one of my factors. So if I were to write this out in factored form, it would be x minus -1, remember? So that's going to end up being plus. So this guy is becoming this factor here. And then this leftover stuff, that's x squared minus 9x plus 20, right? That's what's left over when I divided it. So now, what am I left with? I'm left with a factor that I know what the solution is -1. And then this guy, that's a quadratic. I can solve that. We know how to solve quadratics, right? So from here, 2 factors of 20 that add to -9. Let's see, I can do -4 and -5. So I can make this x minus 4 times x minus 5, and that's an x plus 1. So there's my factored form, and my solutions are -1, +5. Oops, sorry, I forgot to actually make one of those 4, and +4. Okay, and there are my solutions. So what your goal here is you make your list, okay, and then you use that list to just try things until you find something that works where you get a remainder of 0. Okay, and then what's left over, like you just want to keep breaking it down until you have it fully factored. In this case, because I started with a cubic, right, once I pulled out one term, I was left with a quadratic, and we know how to handle those. If I'd started with, like on this guy, with a degree 4, when I pulled that first term out, I'd be left with a cubic, and I wouldn't know what to do with that. So I would keep pulling more solutions out until I found something that worked. Okay, so that's what your goal is. So it's annoying because you have to guess and check, all right? We're going to talk at a later time about how you can be better about guessing and checking, all right? But for right now, that's literally what you're doing, is you're just going to try things until you find something that works and hope that you stumble across it sooner than later, okay? Now, one more quick note with this one. We ended up with 3 solutions here. If instead of using -1 to start with, if I had used 5 or 4, I would have still come out with a remainder of 0, and then you could go from there. So if there's 3 different solutions, you could find any of those 3. It doesn't matter, like they don't have to be found in a particular order.